Hello everyone, welcome back to this week's algebraic graph theory seminar. This week we have Karen Yeats, and she's going to talk about diagonal coefficient of Kirchhoff polynomials of 2k regular graphs and the proof of the C2 completion conjecture.
All right, thank you very much, Tina. So I don't know how many of you guys remember, but the last time I gave a talk in your seminar, it was like the most technically ill-fated talk ever, even though I've been giving talks with this basic technology since before COVID. And by then it was in the middle of COVID and you think we would know how to do it all. But anyway, hopefully this one will be better. So this is what I'm going to talk about. And this is all joint work with Erik Panzer. And there's a paper that we put on the archive fairly recently that you can look at. So part of this is a story that I've told many times before. In fact, part of the reason I'm so excited about this is that it solves a conjecture that I've been trying to solve for a bit over a decade now, but it also is nice beyond that. So hopefully there's something for many different people in here. However, it's going to start with the same story that I often start with. So we're going to define I often just call this the Kirchhoff polynomial, but it's sort of dual to what would be the most obvious Kirchhoff polynomial. And from a quantum field theory perspective, it's sometimes called the first semantic polynomial. So what is it? Given a graph G, you take a sum over all the spanning trees. So that's the sum over all the spanning trees. And you take a monomial, which you make up of the edges that you have to cut to get that spanning tree. So the edges that are not in the tree. And you've chosen a variable for each edge of the graph. And then, and I promise you, this is the only integral that I'm going to write down, and you're not going to have to evaluate it. You define the period or Feynman period of the graph to be this integral, where what you should really think, there's a whole bunch of junk here, but the part you should really think about is just 1 over Kirchhoff polynomial squared. That's somehow morally what the integral is, where you're going over this simplex where all of the variables are greater than or equal to 0. Now you have to put down a few details to make that actually into a correct integral. You would not do very well in your calculus class if you don't write down a differential, for instance. And you will quickly see that that integral is going to diverge for the graphs that we're most interested in. So what you need to do is impose one linear relation between all the variables. And just to keep it simple, I'm just going to set one of them to 1. So what you really want to think of this, if you like to think geometrically, is that morally you'd like to see this as a projective integral, but I might as well write it down on an affine piece because that's how you're going to calculate it in the end anyway. And this is also a good opportunity for me to tell you the kind of graph that I like the most, and this will also set some notation that we're going to use throughout. So the kind of graph I like the most is when you have a graph that's 4 regular and then you remove 1 vertex. And the reason I like that kind of graph is because those graphs correspond to what are known as 4-point graphs in 5-4. So I can think of them as telling a little story about particle interactions, so as Feynman diagrams, but I can also think of them just as pure graph theory. And although the motivation comes from the physics for most of these problems, beyond a few throwaway words like that, I'm not going to say anything about the physics. So you just want to know that those are my favorite graphs, and then my very favorite graphs are the ones where, furthermore, the guy after you have that extra vertex, so the 4 regular guy, is internally 6-edge connected. So the only 4-edge cuts are the ones that just cut off a single vertex. Okay. So why should you care? Well, maybe I will say just a couple of words here about why you should care. And there's sort of different parts to that. So one reason why you should care is that this period is a part of the Feynman integral. And in fact, it's a very particular part. It's the contribution to the beta function, of the theory of the Feynman diagram G. So that's kind of nice. That's actually a thing that you might want to compute in your quantum field theory. It's interesting from the point of view of number theory because interesting numbers show up. So PG, for small graphs, you get multiple zeta values. Then you get other things. You get special values of L functions of modular forms. I didn't write that very well at all. Special values of L functions of modular forms. And you get other things that we don't even know what they are. So you get some really nice numbers out if you're that kind of a number theorist. And if you are like me, and I think probably most people here are, and you're more interested in the combinatorics of it, well, what's sort of the point here is that because this is a sort of generating series for spanning trees, everything you do with this integral you can think of in terms of spanning trees, and well, as you start working with it, spanning forests. So it's all just a game of spanning trees and spanning forests. And that is, of course, how I like to think about it. But I think part of what makes this area so interesting is, in fact, that there's the interplay of all three of these perspectives. And where I say number theory, you could also think algebraic geometry, because again, if you go back to this, if we go back to this integral here, I mean, it's really being controlled. There's just this polynomial that's controlling what's going on. And so I can think of, I mean, that is the world of algebraic geometry. I care about a polynomial, and I care a lot about its zeros, because its zeros are going to determine the behaviors, or the geometry of the vanishing of that polynomial is going to determine the behavior of this integral. And in fact, they ended up getting called periods because it is literally a period integral on that variety. Okay. But now let's do something a little more explicit on the graphy side, because there are some symmetries that this period has. All right. And so, well, notice we had this notation that we had this graph K that was the 4-regular graph, and then we took out a vertex and we called it G, and it doesn't matter which vertex you take out. So if I take a K minus V and I take a K minus W, it doesn't matter. And this, we're going to use this language that K is the completion of G, and G would be a decompletion of K. Of course, the decompletion is not generally unique, so there's no particular reason these graphs should be isomorphic, but sometimes they are. There's other things too. So if you have two graphs that relate by planar dual, so if I have P star, which is the planar dual, P star, how about G star? That would make more sense, right? Graph star is the planar dual of graph. Then the period of the dual is the same as the period of the graph itself. And here's where I guess this is the only word that's slightly about the integral, is I just think that's really cute that this is actually the Fourier transform on the integral, which is kind of cool, because, you know, when you study a Fourier transform, especially if you're sort of a discrete-minded or algebraic-minded person, you're sort of saying, well, that was sort of nice and I passed the exam, but I don't really, you know, have an intuition for it. And I think it's really fun that the Fourier transform ends up being planar duality in this context. Okay, there's some more. There's an operation known as twist. So this is in the completed world. Say you have a graph with a 4-vertex separation. Then you can, with a little Klein 4 group action here, where you just pick two and swap them both. And there's the same period. So that's in the completed world. You now have to remove a vertex on both sides and take the period, and it's the same. There's also a product property. So if I have now just a 3-vertex separation, and this is again in the completed world, then that ends up going to the product of two things. So there's this guy, and now I'm going to put in 3 explicit edges. One here, and one here. So this is one of these things that's slightly annoying to draw. Let me just highlight, this is the blobby part. That's the blob, which is just the graph. And those are 3 explicit edges. Okay, and you get the product of this with this. All right, so these can all be proved fairly readily on the period. You don't actually prove them mostly in the form that I gave it as that integral of 1 over Kirchhoff polynomial squared. There are 3 other forms of that integral, and one of them is more amenable to these sort of calculations. That's the one where you actually literally take a Fourier transform, but these are all readily provable. And so I have been interested now for the better part of a decade, or maybe even slightly more than a decade now, in understanding that period by understanding other graph properties that have these symmetries. And so some of you have probably heard me talk about C2 in the past, and that is excitingly one of them. And we will return to C2 shortly. But I'm going to talk about a different one, a new one, actually. So the key to all of it is going to be this recurrence. All right. So what is this recurrence? I have not actually quite written enough on the slide for you to understand, so I will have to write a little bit more here. And notice I'm going to jump out of the 4 regular case briefly, and I'm going to look at just anything that's 2k regular, so any sort of even number for the regularity. I'm still going to call it k because it's still going to be playing the same role that the 4 regular graph did. And now what I'm interested in is this recurrence. So f is just something, some function on the graphs, and I want it to, I'm going to be very interested in f's that satisfy this recurrence. Okay, but then what the heck is this k tau? The point is you take some matching of some neighborhood of a vertex. So I got a vertex, and it we're going to later do lots of examples for k equals 4. So there'll be, let's say that it has 8 neighbors. And there's some more graph out here, and I don't know what it's doing, but there's some more graph out there. And then what am I going to do? I want to sum over all the ways to just remove that vertex and then replace it with some matching of the neighborhood. So maybe something like this. Right? Doesn't have to be non-crossing, so I won't fake you out by making it non-crossing, but something like that. Okay, now that's a new graph, and that's the k tau. All right, for that particular matching tau. And so I want to sum over all the possibilities, and whenever I have some property of graphs and functions, an invariant of graphs that satisfies this recurrence, that around any vertex, I can just sum over all the ways of resolving that vertex. I'll say I resolved that vertex when I did that. Then that's my recurrence 1, and we're going to come back to that a whole lot. Wait, what's an example of something that satisfies this recurrence? Well, this recurrence came from an observation that Erik Panzer made, that you can take a particular coefficient from the Martin polynomial, and now there's a slight caveat. You have to be careful that you normalize it the correct way, and I will tell you exactly what I mean on the next slide. And then you get something that satisfies that recurrence. So I'm going to define it here recursively, and then we'll see a non-recursive definition on the next slide. So it's going to satisfy the recurrence. So the only thing I need to give you now are some base cases. One of them is going to be that if the graph has a loop, then, and here's some more graph, then it's 0. And that's convenient because if you're in this period context, if you have that, then you, well, your k wasn't internally 6-edge connected, and you should get a 0. That's kind of the right answer. And now we're actually going to use as the base case. Other than that, the base case is going to be when it's when the graph has only 3 vertices. And then the answer is 1. And just parenthetically, because you might want to know what it is when there's only 2 vertices. So that's 2k edges there. Then the answer is 1 over k factorial. But we chose to write it down so that our base case was the 3 vertices, because that makes it really transparent that this m here is always going to take integer values. Except for the 2 vertex guy. And so that's kind of nice, it's always nice to have integers, might count something, things like that. Well, I'm not going to be talking much more about that. Okay, anyway, it's just a normalization. You could normalize it so that the 2k edge was 1, and then you just have some extra factorials flying around that are slightly annoying, but nothing fundamentally has changed. Nothing fundamental has changed. The other reason to use this normalization is, you'll notice if we go back to the operations here, the first 3 are all identities, and so that are homogeneous in number of vertices and things like that. So my choice of normalization actually really doesn't matter there. But this last one, if I want this to be a product on the nose instead of having some extra little factorial factors, then I have to choose the normalization that we have on the other page. Okay, but in any case, here's something that defines some item. You may have no intuition for it, but it defines something. And it turns out that this thing does, in fact, satisfy the period symmetries. And in fact, the proofs are not that complicated. Mostly you basically just sort of work through recursively. The key is, you have the recurrence 1, and you reduce variables on, so you reduce out a vertex on one side or the other and see what happens. Okay, I'm not going to go into those proofs though, but you can read them. They're all in the paper. All right. Now, some of you might have, if you like your graph polynomials, you might have thought about the Martin polynomial at some point. I think it's a tad old-fashioned at the moment, but it's a perfectly nice polynomial. There's a few different normalizations again and a few different choices of variable, but I'm going to define it this way. Where I'm going to say this Martin polynomial, which I'm going to call lowercase m of a graph, and it's a polynomial in the variable x, is going to be, well, I'm going to take some sum, and I'm going to say I'm resolving every vertex. So what does that mean, really? Let's say I have a nice small example like this. There's a perfectly good graph. And now I want to do every resolution at both vertices. So there's all three possibilities at both vertices. All right, so I'm not going to maybe bother you by drawing all of them, but here maybe one of the things I would get is that. One of the things I would get is that. Another one of the things I would get is that, and then so on. Well, you get the idea. I guess I can draw some more of them while I'm talking, or maybe I can't, depending on how coordinated I am, etc. And in each case, you just count how many connected components you have, right? So this one has 3 connected components, 2 connected components, 2 connected components. Okay, I didn't draw any of the ones that have 1 connected component, but of course, some of them will, things like that. And so you just literally make that sum based on the number of connected components. Okay, and now then, for a graph that's 2k regular, you can get this Martin invariant out of a certain coefficient. And here's where you have to do 2 slightly annoying things. You do have to change the variable, and it's not a constant coefficient. You have to take a derivative. So it's a linear coefficient once you've changed the variable. And there's still an annoying factorial factor at the front, but that's because we chose to normalize it. We could have chosen to normalize it in the way that most naturally comes straight out of the Martin polynomial, but that isn't as convenient for everything else we wanted to do. Okay, actually, before I move on to diagonal coefficients, are there any questions about the setup so far? All right. Well, seeing none, then you will have to put up with diagonal coefficients. So the key to all of this, to making the connection to the C2 invariant, to proving the old theorem that I've been wanting to prove for a long time, proving the old conjecture, is to actually look at this particular diagonal coefficient. So we have our Kirchhoff polynomial, or our dual Kirchhoff polynomial, really, again. Whenever we're in sort of Kirchhoff land, we've always removed the vertex. So we have our k, and we've removed the vertex. And now we're going to take it to an appropriate power kr. And then what I want to do is I want to take, well, what is this? I'm calling this a diagonal coefficient. So what do I mean? I've got all of the variables here. So n is your number of vertices. And so then this is going to be your total number of edges. So I've got all the variables appearing, and all the variables are appearing to the same power. And that's all I mean by diagonal coefficient. And okay, what power is this? You say that looks kind of ugly, but the point is it's the power that it needs to be in order to possibly be a monomial in there, because this guy's homogeneous. So there's only one monomial where they all come to the same power that's possible. And it's this one, as it turns out. So this is more ugly than it sort of looks like it should be, but it is the diagonal coefficient that can be in here. And now the key is this diagonal coefficient, that's some number, it satisfies the recurrence 1. And since it satisfies the recurrence 1, it only differs from the Martin invariant by a normalization. And here's the particular normalization that you need. You need a factorial over here and a little factorial over here, but fundamentally, there's always annoying factorials in this story, so you can just basically ignore them. Fundamentally, this diagonal coefficient is essentially giving you the Martin. And now this notation here, this is the notation. This is something that's going to come up a fair bit for us. This is R duplicating the graph. And so what does that mean? It means everywhere where there used to be an edge, I want to replace it with an R multi-edge. All right, and for all edges. So that's what I mean by R duplication. All right, now this is really the key. And no matter what hat you're wearing, this is interesting. So if you put on your algebraic geometry hat, this is particularly interesting because there's stuff that algebraic geometers know about diagonal coefficients and some of their behavior. And in fact, there's going to be some exciting new work out with Erik and another collaborator, which hopefully will pursue that direction and get something pretty exciting, I think. But I'm not going to tell you about that. I'm going to tell you about the thing that's exciting that we have already proved. So I said I wanted to show something about C2. And I obviously skipped a page. Okay. I said I want to tell you something about C2, so I need to tell you what C2 is. So what is this thing? I'm going to take a prime P. That's here. Oops. That's not what I wanted to do. I wanted to do this. I'm going to take a prime P. Now I'm back to the situation where my K is 4 regular and my G is still K minus V. And now what am I going to do? So these are my favorite graphs again. I'm going to say that the C2 invariant at P of G is you take the Kirchhoff polynomial or the dual Kirchhoff polynomial. And now what is this notation? This is some point count over the finite field FP. So you're now back to putting on your algebraic geometer hat, and you're thinking of this as a variety, the set of points where this polynomial is 0. But now I'm thinking of it over this finite field. And if you don't have an algebraic geometer hat, because I know not everyone has one of those in the closet, this is actually extremely concrete, right? You're just plugging in numbers 0 to P minus 1 and seeing when, after you plug them into this polynomial, you get 0 mod P. That's all that's going on. Very, very concrete. Anyway, it turns out as long as the graph has at least 3 vertices, then this number is always divisible by P squared. And so we want to divide it by P squared and take it mod P. And now that is your C2 invariant. I'm going to highlight it correctly instead of incorrectly, but hopefully I'm going to highlight it correctly because that's really important. Okay, but so I said it was important, but why is it important? I mean, what do you care, right? Like that's some sort of weird thing. And if you've heard me talk about it before, you've heard this story before, but I want to just take a moment to tell you why you should think this is important. And it also will help you remember why it's called C2. So the reason why you should care is that early computations of the period were all multiple zeta values. They could all be expressed as linear combinations of multiple zeta values. Now it's no longer the case, right? Now we have other periods that we know are other things. I mean, and no is a little bit strong here because of course it's very hard to show that there are not hidden relations that you don't know about. A lot of the big conjectures in this world, in the whole story of transcendence are about that. But assuming that there's not some giant conspiracy in the transcendentality of the universe, then then we now know that it's not true that they're all multiple zeta values. But early on, when these things were computed, all the ones that were computed were multiple zeta values, and so it was plausible to think maybe they were all multiple zeta values. And if they were all multiple zeta values, then they should all be multiple zeta values for some good mathematical reason, right? Not because of just some sort of weird conspiracy. And again, if you have an algebraic geometer hat, you might know something about what that good mathematical reason ought to be. And in fact, in the language of motives, then answer should be that all of these varieties are mixed-Tate motives. And so, smart people saw this, and in particular, Maxim Kontsevich saw this. And furthermore, if these varieties were all mixed-Tate, then something very special would happen when you take this point count. Because part of this whole yoga is that if the geometry in some suitably abstract, i.e. some motivic sense, is sufficiently nice, then it should be nice both when you're thinking of it over some field of characteristic 0, but also over some finite field. And so one of the consequences of this is that this point count, just this guy here, would be a polynomial in P. So if this is always true, oops, spell it right. Good to spell things right. It should be for some good mathematical reason. The reason would be motivic, and it would imply that this thing is a polynomial in P. And if it were a polynomial in P, this would be the quadratic coefficient, and in fact, it would be the smallest coefficient that is at least potentially non-zero. So we're pulling out the lowest coefficient that could be interesting. So C2 is the quadratic coefficient. And C2 would in particular not depend on P. It would just be some constant. Okay, but this is not true. So false. But the C2 invariant remains a good measure for how false it is for a particular graph. Because for some graphs, this is a constant. For some graphs, the point count really is a polynomial, and so the C2 really is a constant. And those are graphs that have particularly nice periods. And so it's now becomes, the C2 becomes a measure of how false it is. And so it tells you something about what kinds of numbers you should see in the period. So C2 remains a measure of how false. How false. And hence how exotic the PG are going to be. And so that's why it's interesting. And it's also interesting even in practice, even if what you really want to do is actually just compute PGs because you're a physicist and you want to know about the beta function of your theory, because practical computations of these things are not usually done analytically. They're usually done numerically and then using something like PSLQ or related methods to find what the analytic form would be. And so then if you have some idea what space you're pulling from, that helps you an awful lot. Anyway, that's the story. And that's the story of why, especially if you're wearing your algebraic geometer hat, but even not, you should be interested. Okay. Now, it turns out that C2 can also be expressed in terms of diagonal coefficients. And this is something that Simone Hu and I, who many of you know, had worked on quite a bit. It was the result, one of the results from her master's thesis here was showing the completion conjecture for C2 just in the case when the prime P equals 2. The technique we used was, well, it used this slightly more complicated polynomial that I mentioned here. So it was not just the Kirchhoff, it was some other polynomials that are in terms of spanning forests with certain properties. But that's a detail for the level that I want to tell the story today. And it turns out that in fact, at least for P not equal to 3, you can actually express the C2 invariant as the diagonal coefficient of this dual Kirchhoff that we started with. And so here's the actual formula. You can see here there's an obnoxious extra P, extra 3. And so not surprisingly, when P equals 3, things are going to go wrong. And then you have to go back and work with that other polynomial. So if you ever saw another talk of mine, and I was talking about something that looked like this, that's the polynomial I'm talking about, that particular product. But I'm not going to go into that guy today. Anyway, the consequence of this is C2 is expressible in terms of the diagonal coefficient. The diagonal coefficient satisfied that recurrence. And so since it satisfied that recurrence, it differed from the Martin invariant only by some normalization. And so C2 differs from Martin only by a normalization. And specifically, you get this formula down here. And this is really the key. So the C2 at the prime P of the graph, the D-completed graph, so the K minus a vertex, is the Martin of that graph. And now here, because we had this extra power here, that turns into K duplicating or P minus 1 duplicating the edges of the graph. So I take this completed graph, I replace each edge with P minus 1 copies of the edge. I take the Martin of that, and what I normalize by is just a 3P. And not surprisingly, again, you see that P equals 3 is going to be a little bit of trouble, and you have to make a different argument in that case. And it's more intricate, but it's not fundamentally so different. You have a bunch of extra junk to keep track of, as you know, as these things sometimes go. So that is super exciting. So now C2 is this invariant we've been interested in for a long time because there are these Kontsevich style good mathematical reasons why we should care about it. This Martin is something new and a little bit more, unclear what it really says about the physics or about the algebraic geometry, but it seems to be really accessible because of this recurrence. And so we can show that they agree using this little lemma up here. And notice that this immediately proves the completion conjecture for C2. I think that's what I said here at the top. C2 was conjectured to have all the period symmetries, but will that conjecture for for completion in particular was over 10 years old. And honestly, smart people had tried to work on this using tools of algebraic geometry and using tools from mathematical physics, and really were not pretty well getting anywhere. And I would have to say, I think the only real progress on that proof was my work and then my work with Simone, where we did it in the case that p equals 2. And we did it in the case p equals 2 by sort of chasing around the spanning trees and the spanning forest, like really explicitly. As long as you had 2 hours to sit down, it was completely elementary. Now, this is not as elementary, but notice immediately you get completion, because on this side, look, I have k minus v, and on this side, I don't have k minus v, I just have k. There's no v on the other side at all. So completion is completely immediate. So that's nice. So, yeah, so that's the proof of the completion conjecture. I mean, I haven't told you how to prove those lemmas, but I will come back to that, because given that there's time. So that you'll be able to see some of the actual core business of the proof. Okay, you might possibly, I don't know how many people here in the audience have been hanging around long enough to have heard me talk about this other invariant that comes from the permanent, but it can also be expressed as a diagonal coefficient. And so similarly, it now relates to Martin. So this Martin, and in particular this Martin recurrence, and the fact that it connects to this diagonal coefficient, has actually given us a way to unify almost all of the period invariants that we understood. Okay, then I want to take my last bit of time to actually give you a sketch of how the key part of this proof goes. But before I jump onto that, let me just see if there are any questions about what the results are and why we might care, before I jump on to telling you something, which I think you'll really like. It's actually it's pretty and elementary about the proof. All right. So what's kind of cute about this is that the proof basically ends up coming down to something really classic that you probably taught to students, and that is the proof for encoding of a labeled tree. So I just want to recall what the classic proof for encoding is first, because then we're going to use it. All right. So what is the algorithm? Let's do an example, but I'll also write down what the algorithm is. So here's a tree. This is an algorithm for a labeled but not rooted tree. So let's there's a thing. And now what do we do to make the proof for code? We're going to start with I equals 1, and then there's a thing that we repeat. And what is the thing that we repeat? We're going to pick the smallest leaf that's left. And that's smallest in terms of the labels. So you do need a total order on your labels to do a proof for encoding. So pick the smallest leaf. We're going to call it AI. And we're going to let BI be the neighbor. And now what am I going to do? I'm going to remove AI from the tree and increment I. And then what is my proof for code? It is just the B's. And if my tree had n vertices, you can quickly see that you're going to get n minus 2 things in here, because at the very last step, you won't be, well, you don't need to encode the very last step, basically. There's no new information at that point, because there's just 2 vertices and they have to connect. And then what, if you taught this in your class, you will remember is that it turns out that you get every B in 1 through n in the, the potential things, the number of vertices, the n minus 2. So yeah, sorry. I said the labels had to be totally ordered, but if you want this last part to be true, they have to be not only totally ordered, but they have to be 1 through n. Anyway, you get everyone exactly once. And so that's one of the classic proofs of Cayley's formula for the number of labeled rooted trees. Labeled non-rooted, labeled just free trees. Okay, fine. Let's just do this in this example so that we have it all fresh in our heads. So what's going to happen? So I'm going to start with I equals 1. So my A1 is going to be, so it's the smallest leaf that's here. So that looks like 3. And then that means that B1 is going to be 1. Okay. And now I'm going to get rid of 3. All right. And now I'm going to have, now I'm at I equals 2. So A2, let's see, the next smallest leaf is 4. And so then B2 is also 1. And now I'm going to get rid of this leaf. Okay, and now what is my next smallest leaf? Well, now my next smallest leaf is actually the 1, because 1 is a leaf now. So A3 is 1. And B3 is, well, 2. Okay, so we'll get rid of this. And now I'm left with just 2 vertices, so nothing interesting is happening anymore. And so my proof for code is 1, 1, 2. And so it turns out that everything happens exactly once. And how do I briefly sketch that out? Well, you can reverse the algorithm as follows. You put these guys, and I know you're like, I know this already, but it's just helpful to go through it in order to see how the proof we want in a second goes. And what do? You put outgoing edges one more than the number of times that appears in the list here, in the code here. So 1 appears twice, so I put 3. 2 appears once, so I put 2, 1, 1, 1. And now at each step, I say I take the smallest thing that has only one guy left, and I connect it to where the sequence tells me it should go. So 3 goes to 1, that takes care of this. 4 goes to 1, that takes care of this. And 1 now is the smallest one that has only one thing, and that goes to 2 because that's what it told me to do. And now there's only one thing, so you join it up. Okay, that's the classic proof for encoding. Okay, now let's think about that diagonal coefficient. So let me just go back and get the diagonal coefficient. Let's think about this guy for a moment. Here's the diagonal coefficient. Now remember, this is essentially a generating series for spanning trees, where we put the monomial of the edges that are not in the tree. Well, I could always dualize everything and put the monomial of edges that are in the tree. It's not really going to matter in the end. So what are we really doing when we take this monomial? We have here 2p-2 copies of each edge, and we want to find monomials that are the complements of spanning trees, or complementary. We want to find monomials that are spanning trees. And how many of them do we want to find? We want to find p-1 of them. So really what this is partitions of 2p-2 copies of the edges of G, into p-1 spanning trees. So I said it was all just about spanning trees, right? Oh, we did all this stuff, and we said words about physics and algebraic geometry, but really, we're just partitioning copies of the edges into spanning trees. Okay, well, that's kind of nice. So here we are. So let's say we're in that situation. So I'm going to take the specific example. I'm going to take a specific example. Let's say G is 8 regular. Let's say V is a vertex with no loops. We actually need that. Well, we don't need that, but it's more complicated if it does have loops, and I don't want to go into that. And let's say we have a partition of the edges of G into 4 spanning trees. Okay, well, what could happen? Consider what's going around V. Consider the neighborhood of V. And so here's an example of one thing that could happen around V. So okay, not an EQ, but an EG. One. It'll be useful later to number these guys. These are that's obviously not right. 5, 6, 7, 8. That's the problem of talking at the same time, and this is V. So here is the neighborhood of V. I've just labeled them because that'll be convenient. And remember, we're going to have 4 of these because we partitioned the edges into 4 spanning trees. So here's my 4 copies of this little area. And let's just for the sake of argument, let's say in this one, we use this edge. This one, we use this edge. This one, we use these 2 edges. And say here we use these 4 edges. All right. That's certainly one possibility. And then I also want to, for example, just say what I need to know about, what do I want to know about the rest of the trees? Because I don't actually care about the specific shape of the rest of the trees, but I do care about which vertices they connect. So when there's only one edge into V, so V was a leaf in the tree, then I know that whatever else happens, everything else has to get connected together, right? The tree just connects everything else up. So here as well, the tree connects everything else up. Now here, though, the rest of the tree is going to partition these other vertices into two parts, one that goes with 3 and one that goes with 4. And just for the sake of argument, because I need to pick something, let's just say it gives this partition. And likewise, this then gives the complementary partition. And here, well, again, I just have to pick something. So I picked that, and this guy stood alone, and this guy did this. So what is the point here? The point is that, well, exactly what it says here in the top. Trees partition the neighborhood into systems of distinct representatives. So I have some partitions. So get partitions of the neighborhoods. V, and what are they? Well, let's call this one P1. P1 is the boring partition because they're all just in the same part. And that's also P2. So this is for P1, P2. Now, I don't know if you can tell clearly what I tried to draw here, but I wanted P3 to be the partition where 1, 4, 5, and 6 are in one part, and the other part is 2, 3, 7, and 8. And then that leaves for P4 is the partition 1, 2, 8, 3, 6, 4, 5, and just 7 alone. Okay. And now I want to define, well, a function. So, okay, I've said what the partitions are. I haven't said what the system of distinct representatives is. That means, what is a system of distinct representatives for a partition, or for a series of partitions here? I need to, well, a representative is I pick one representative from each part. So one from the one part of P1, one from the one part of P2, one from this part of P3, one from the other part of P3, and one from each part of P4. And it's a system as a whole because they have to exactly give each element of the neighborhood once. That's just exactly what these edges are doing. But it's just another way of saying the same thing. And I'm going to represent this with a function f. And what is f going to do? F is going to tell you, so 1, it's because I have to be partitioning the neighborhood, 1 has to belong to somebody. Who does 1 belong to? Well, 1 belongs to number 1 here, because 1 is my choice of representative for here. F of 2 is also 2. So far that's kind of boring because, well, yeah, I chose 2 here. Now, F of 3, where's 3 showing up? 3 is here, but my choice of representative here, and here I chose 4. So F of 3 is 3, and F of 4 is also 3, because they're both coming from P3. F of 5 is 4, F of 6 is 4, F7 of 4, and F of 8 is 4, all right? Oh, I'll write a little better than that. F of 7 is 4, and F of 8 is 4. And that's, look, I chose the numbering so that it did that, right? So I chose 5, 6, 7, 8. Those are my representatives. Okay, I just encoded it in a function. All right, we're almost done. Because now we just have to think about what happens on the other side of the picture, right? What do I do in that recurrence? Let's go back to our recurrence, which showed up in here somewhere. No, sorry, that's slightly too far back. Here it is. What did I do? I took the neighborhood of the vertex and I replaced it by a matching. Okay. So what does that look like in our picture that we had before? What information do we have about the neighborhood? Well, the information we have about the neighborhood is these partitions. So let's collect this and bring that to the other page. So what have I got now? All right, I got a spare n that I'm not going to be able to erase in a reasonable way, but I don't have these anymore, and I don't have v anymore at all. So what I have are these partitions. And what do I need to do? I need to pick edges of a matching so that each of these turn into trees. So these two only have one part. This only has one part. Now, this has two parts. So I need to add an edge somewhere to turn it into a tree. And these guys here, I need to add, this has four parts. So I need to add three edges to turn it into a tree. All right, and you will not be surprised to find that I did not pick these edges randomly. So turn the matching to contribute to the recurrence one turns the partitions into trees. Okay, but look, if I have trees, there's something I know what to do with them. If I have a tree, I can do the proof for encoding. And so I need now two pieces of information. So these ones here that just have one part, I do nothing. Because they only have one part. So we're just going to ignore them. They're done. But on the other, for each of these, I want to do two things. I want to write down the proof for code, which I'm going to call Y. And I want to write down which specific vertices are involved here. Which ones are actually the ends of the matching. Because the proof for code, it only knows, like, it's treating each part of the partition as a vertex, a big fat vertex. So it doesn't know that information. So that I'm just going to keep in a set. X4. I'm going to keep in a set 5, 6, 7, 8. And I'm going to make the proof for code. And now I can take, well, okay, here the proof for code is empty. There's only two parts. There's nothing. Here, this one's slightly more interesting. So let's check out this one. So what's going to happen? I'm going to order the parts by their smallest entry. So then the smallest leaf is this 4, 5. Sorry, I'm going to order the, oh, did I do it backwards? No, hopefully I did it the right way around. That's all. Anyway, I'm going to order these leaves. So this by their smallest entries. Oh, I don't remember. Yeah, anyway, okay, hopefully we'll get it right. So here I got 3 as the smallest entry and it goes to 2. So I'm going to put the 2 there. Here, 4 is the smallest entry. It's going to, once I've removed that, it's now the leaf with the smallest entry. And so it goes over here to the 1. And that's my code. Okay. Now how do I go back the other way? So what do we have here? I want to say that this corresponds to the other one. And hopefully I haven't messed anything up. So what I'm going to do, because I have really, well, let's go look at the previous page again. What's really the information? I need to know where everyone matches up. So I need to know how to make this F basically out of the proof for code. And so here's what I'm going to do. I'm going to define F as follows. So for I, so I'm going to say R is the number of these guys that have only one part. So R equals number with one part, which in this case equals 2. And if I is greater than R, I'm going to get let F of A equals I for all A in Xi. And for I less than or equal to R, I'm going to let F of B equal I for B, the ith entry of the concatenation of the Y's. So Y R plus 1, Y R plus 2, etc. And so let's look at that in this case. So if it's bigger than R, so if it's bigger than 2, I just say, well, which X was it in? Okay, so 3 and 4 are in 3, 5, 6, 7, 8 are in 4. Let's go back to the other page. 3 and 4 are 3, 5, 6, 7, 8 are 4. And then otherwise, I just have to have the 1. I just read them right off of the y. And here's where I think I did this backwards. So I think I just need to fix this guy. Sorry about that. And then I will get it the right way around. I think I counted it wrong the last time I did it, because the point is I just concatenate empty with 1, 2. And so I read off 1 for this and 2 for that. And that's the story. Anyway, I'm sure you didn't catch all those details, but the point is it's just a little game with proof encodings. And that's kind of cute. And what that shows then is that that diagonal coefficient, which is really just counting the number of edge partitions of 2p minus 2 copies of the edges into p minus 1 spanning trees, that satisfies that Martin recurrence, the recurrence 1. And that's the big step. Once you know that that satisfies the right thing, then you know the diagonal coefficient equals Martin. And we already knew through other means that the C2 could be expressed in terms of the diagonal coefficient. So that's the thing that links it all together. And then the rest is details. Somehow it ended up being 60 pages of details, but you know, that's how papers go sometimes. Anyway, I'll stop here. Thank you very much, everyone.
Thank you, Karen.